Welcome everyone. As said, my name is Christian. I've been working for time and frequency for 30 years. It will not be an easy task here to explain time and frequency on this kind of level that I will try to do just before lunch. You may be tired and hungry, but I will try anyway. This is the outline of my speech or presentation today. So I will tell you a bit why we are doing what we're doing. I will present some of the clocks and the difference between clocks and oscillators. We will talk about national distribution, as well as we can have some questions afterwards, if you're not too hungry. If you should remember any slide today from my presentation, this is the one. This is the most important one I will show you today. This is how we distribute time and frequency within Sweden. So here we have the national timescale, UTC-SP, at the National Meteorology Institute. Don't get confused by the arrow here. We only have traceability. We don't take time from those guys. We have our own services. So we have redundant sites for distribution of time and frequency of different kind of sources. Then we distribute time and frequency to the society. We do it to autonomy and positioning, as well as aviation, defense, economics. We take part in EU projects. We give time and frequency or synchronization to storage. We have some research. But not least, we have the energy sector. They are really in need of time and frequency. And we have the authorities as well. So this is kind of a short background to the time and frequency within a country. In this example from Sweden. So in the early 1800s, everyone looked at the sun and said, okay, it's 12 noon, since the sun was in the south. But if you do that on two locations, like in Stockholm and Gothenburg, it differs about 24 minutes. It doesn't matter if you're only doing regional stuff, but the introduction of the railway made it really hard. They needed to set off the train at the timetable, which means that they need to have the same time. So we started to have the first national Swedish time in 1879, called the railway time. And it was set to a location in between Stockholm and Gothenburg, called Laxå. Okay, so now we have the Swedish national time, but still we needed to communicate with other countries, which means that we follow Greenwich Mean Time. And that was the time set to the observatory in Greenwich when the sun was in the south. But we couldn't just follow that, so we add an hour. So we had GMT plus 1 hour, as well as the Danish had. Well, they call it Bornholmstid. In 1972, this definition changed to having atomic clocks. And based on that, and also they adjust for the Earth rotation. So I'm talking about atomic clocks. There are several kinds of those. I will present some of them later on. But the definition of the second nowadays is based on cesium since 1972. And it's the cesium-133 atom. And we are counting periods, since if you get it to jump between hyperthin states, it will either absorb or emit some radiation. And if you count that radiation and set the number of counts to whatever you like, you can have a second. In our case, we have 9,192,637,770 periods. That's 1 second. And the reason for not being 771 is we wanted to have the same it will follow the old definition from the sun and earth and so on. So atomic clocks, Sweden is a small country. We are not developing our own clocks. We are buying commercial ones. So since I work at BalticNOG, we are using the commercial cesium clocks for our sites. They are fairly good. They have a drift about a second in 300,000 years. That's not too bad, but it's not enough. So we can have hydrogen masers as well, also commercial, a weight of roughly 300 kilos. But I guess most of you doing network and telecom stuff and other kind of technology using these miniature atomic clocks like rubidium clocks. They are not as good as the other one regarding stability. And I will present some more about stability later on. But still, we have these clocks around the globe, but we need to have some even better clocks. So they are called cesium fountains. We call them primary clocks. And the reason for not just having these, you need to have a lot of manpower to have them working. They're working maybe a month, a year, but then you do really good measurements. So you will see the connection between all these clocks later on also. As I said, the definition of the second now is based on cesium-133. We are in the progress of redefining the second, and then we will use optical clocks. They don't work for a long time, a week maybe at a time. So this is a strontium clock. Yeah, it's a lot of equipment. Just to give you an insight of the cesium beam tube, since we're using those as the standards, you have the atom source, you heat atoms, you have them propagate through the Ramsey cavity, you trap them, you set them in the right state, then you detect them, and you steer your microwave source. Up to the right, you have the cesium beam tube, as it's in the clocks, and on the down there you have it taken apart. These are not radioactive at all. So we have some guys, Isidore Rabi and Norman Ramsey. They were really inventive, so they invented the cesium beam tubes. And as I said before, they have a frequency of about 9.7 gigahertz. It's an old technology. It was invented in the 1950s. Norman Ramsey also went to doing hydrogen masers, and maser is more or less a laser before it starts lasing. It has a lot less, it's only 1.4 gigahertz to be able to work. Then we have these cesium fountains, and I really found these cool. So what you do, you trap the ions with the lasers. You move them upwards with another laser. You let them fall down, and then you probe. It seems like an easy process, but it's not. It's really, really hard to set all the lasers, to actually be able to probe them, and also have them in this cloud. Those previous clocks I presented here aren't good enough. When I started working with time and frequency, they were really, really good. But what we are seeing, the community is in need of better frequency or more stable frequency, more stable time, which means that we are heading to optical references instead. So we're looking into, there are two main types of optical clocks. We have the optical lattice clock, which is an ensemble of trapped atoms. They are mainly used for frequency measurements. And then we have the single ion trapped clock, also for frequency. We always measure frequency and then we do time from that. Up in the Scandinavian countries, the only optical clocks that is running as for the moment is based in Espoo at Mikke's lab. Anders Wallin is operating it. I would like to have one in Sweden, but they are really costly. So, as I said before, we are in progress of redefining the second. We're looking into several hyperthin levels and different kind of atoms or ions to be used. And the reason for going for optical references is you have a higher frequency, which increase your accuracy. Still, it's a long way. I believe in 2030 or something, we will be able to actually decide which kind of references we should have. For the moment, the only guys who are using these optical clocks are scientific experiments or observations, as well as some of the navigation and positioning systems. Yep. So I have been talking about stability. Just to give you an insight, for time and frequency, we always try to describe our oscillators, clocks, links, transmissions, and so on with some statistic graphs. So in this case, we call was a guy, Dave Allen. He took this M sample variance. He will set the M to 2, and we are able to say how stable our clocks or transmissions are. So when we talk to a couple of parts 10 to minus 11, you see the bottom of the graph there, and also you have an uncertainty or error bars. We all also like to know about the flicker phase noise and white phase noise. So if we apply a low-pass filter on the previous statistics, you can show which kind of noise errors you have. This is a really interesting picture as well. The best commercial clocks are the Masers. Don't care about the names here, but you can see in a day they reach a couple of parts 10 to the minus 15. And the clocks we are using for distribution for telecom, energy, and authorities are the blue line here. That's a commercial HP 5071As. The reason for using those, they have a small form factor, they're not that heavy, and they have a lifetime of about 10 years or more. A lot of technologies are using these GPS discipline oscillators. They're really good, but still they're disciplined to satellite-based systems. You will also see this abbreviation, UTC. It stands for Universal Time Coordinated Time. It's dependent on how you spell it out. UTC is just a paper clock, which means that you take more than 400 clocks at 80 locations around the globe. You measure them, you send the data to BIPM in Paris, and after a month you get the result back telling you how good or worse your clock were a month ago. Yeah, it's of no use actually for the end user. So they have tried to have this UTC-R, it's a rapid one, and then you get a result back within a week. But what we are doing in the timing community, we are doing realizations like UTC-K. UTC stands in Sweden for SP. So we predict, we measure, and we steer our timescales. Since that timescale is steered, means that I'm steering my clocks at NetNode as well for the distribution to the community. UTC is just a map of the most of the labs participating in creating UTC, the atomic timescale. So this is how it's working. You have data from 400 clocks or more. You have a weighted average. You have a mathematical algorithm to determine the weight. Then you get a free atomic timescale that is free steer from the Earth rotation. You apply steering from the primary secondary sources like the fountains. Then you get TAI, atomic time. Then we have data from the observatories or International Earth Rotation Services, which is telling us to add or subtract a leap second. Then we can have the UTC. The data goes back to the guys doing UTC-K realization, and they are able to steer their clocks. Since 1972, we have added leap seconds, since the Earth has been moving faster, but lately we can see some tendencies that it's slowing down, which means that we might need to subtract a second within a couple of years or so. There is a proposition to stop adding leap seconds. So if we just do that, more or less, night will be day and so on in a couple of million years. So it's not my issue. We're talking time transfer equipment. Most of you know about doing it in fibers and so on. The most common way of doing really good time transfer is using GNSS. GNSS stands for Global Navigation Satellite Systems like GPS, Galileo, Beidou, GLONASS. We look at the same satellites, and some for the really high-end satellite comparisons, we use two-way satellite time and frequency transfer using a stationary geocommunication satellite. Just give you a brief insight. So for GNSS, common view, we look at all satellites in sight. We compare the time from the system with our local clock. They do the same at site B with a local clock at site B. And then we exchange the data and are able to actually subtract the GNSS time. It's actually removed. This will give you an uncertainty of roughly a nanosecond. Two-way satellite time frequency transfer is you're in need of more equipment, really big satellite dishes. In this case, you're actually sending time from location A to location B and vice versa. So on the right here, you see one of the stations in Sweden. It's a 1.8 meter dish. It's more or less looking down in the ground, since Sweden is not a really good country to have this communication with those satellites around the middle of the Earth. And in Finland, they have it up on the tower, on the top of the tower. We get a lot better uncertainty. We have less than 1 nanosecond uncertainty and frequency stability better than 10 to the minus 15. We are now in the progress of using this kind of equipment and doing it in a passive way. So everyone that have a smaller dish could just eavesdrop some of on the communication and do this kind in a passive way. But we are not there so far. The reason for this is up in the Scandinavian countries, we have 3 timescales. We have the one in Norway, JV. We have the one in Finland, UTC Mikes, and SP in Sweden. Denmark are in the progress of creating one, and then we have one here in Lithuania. Unfortunately, I don't have a connection down here, but maybe in the future. So no one will actually pay for this. So we have an ordinance in Sweden. Otherwise, everyone, I don't care. It's not my business. Someone else should do it. But ordinance telling that rice the National Meteorology Institute, are responsible for distributing the Swedish national time. They should also do international comparisons. They steer the UTC-K or UTC-SP realization within plus minus 5 nanoseconds. That's fairly good. They also need to supply me with traceability at NetNode. And then they do some research, knowledge transfer, and all that. But their main tasks is to do international comparisons. As for last week, they participated in, as I said before, more than 400 clocks. They have roughly 17. They are participating in this UTC timescale. This is a site in Borås, and they have, in this case, Maser, 3 cesiums, and also the timescales up in the top of the racks. They have redundant sites, so they have a site in Stockholm, and also we use Onsala Space Observatory as a third backup. And then you might wonder why Onsala Space Observatory has some good clocks. They do VLBI, very long baseline interferometry, which means that they need to timestamp the data really, really well to be able to compare it with other observatories later on. So I have been talking a lot, but this is how you create the Swedish timescale. You have a lot of clocks, you create a group clock, you apply a correction, then you have the timescale UTC-SP. You do international comparisons with different kind of methods. In this case, we are only telling that we are doing satellite-based ones, but we also do fiber-based ones. We get some measurements back from UTC, and our measurements, we apply correction and steer our timescale. We don't touch the clocks, we just start them and let them go. So we have also NetNode have the same kind of setup. We don't have masers, but we have a master clock, we have an AOG or an HROG, which actually it's just a simple micro stepper that we are steering the time out from. And if you're more interested, you can go into BIPM, Bureau of Weight and Measurements, and look at the site of all these 400 clocks. But from Sweden, we're participating with 17 as for the moment. Some old graph, just to show how the times are varying. In blue, we have the Swedish time scale. In gray, we have the Finnish one. And in green, with orange dots, we have the Norwegian one. As you can see, they had some issues with the labs during this time period. But normally, we steer all timescales within plus minus 40 nanoseconds or something. Then we need to, it's really, really good that we have these nice labs and setups, but we need to get out to the community, so we do it by NTP. It's a simple protocol. It's self-declared quality about it. I don't really like it in that kind of way. You need to be sure that you connect to a trusted NTP server. Then a couple of years, years ago, about 20, we got PDP, Precision Time Protocol instead. The difference here is you need to have special equipment on both sides to be able to do these comparisons. We have White Rabbit, developed at CERN, the Large Hadron Collider. They needed to actually synchronize their own clocks, so they took PDP and made a profile for time and frequency. You can do this in the same fiber, bidirectional, or in duplex fibers. It's still really, really good. Then we have some customized time transfer protocols as ELSTAB from Poland. And also we have Nimbra time node. So far I haven't seen a reviewed paper on Nimbra time nodes, but maybe in the future. So dissemination in Sweden then. We have high performance clocks in 3 cities. Here presented in blue circles. We compare them by using GNSS or fibers. This is an old slide, but we have fibers in between, so we are able to compare them. And then we distribute NTP, PDP, and GNSS, and so on. The reason for us doing this, for the Swedish Post and Telecom Agency to finance it, is that they were in need for the telecom companies to have accurate time. Also, our sites are designed for the blue circles here to be able to be better than a microsecond for 30 days. And my sites at NatNord, we will follow ePRTC for about 90 days. Many of you have seen this kind of oscillator or used it. It's a GPS disciplined oscillator. They're really good. You need to be sure that you're not spoofed or jammed in some kind of way. Otherwise, they are really, really good, as you saw on the previous slide. But still, the traceability isn't defined regarding to all measurement standards. So we don't use it. So why am I here talking to you guys about time and frequency? At least the society have developed really, and we are dependent on really good time and frequency for transportations, for electronic communications, and every other systems we're in use of. So all electronic communications need time of different kind of accuracy. Not everyone need a nanosecond. It might be 10 seconds, but for some parts it's better when a microsecond. So that's the reason for us doing this. Also, we know that GNSS could be spoofed, jammed, and so on, or disrupted. Could be intentionally, it could be unintentionally. So that's the reason for us to have these sites and distribute time and frequency over existing networks. The goal from our funding agency is to have an independent system to GNSS. We should be sure that it's robust and have secure time. We should be able to distribute it throughout the whole of Sweden. It's 1900 kilometers between the southern part and the northern part of Sweden, so it's a long country in that kind of way. It should be affordable for the users to connect. And also, we need to have transparency of what we are doing to regulatory authorities. That means that we need to be based in Sweden. But still, we're able to distribute to other countries also. And I will show you the most recent thing we're doing. One of the questions yesterday here talked about how we are using our nodes. And as seen here, we have redundancy. It's 2 equal sites. We have the clocks, we have microsteppers, we have the measurement unit, and also we have distribution units, we have PDP, NTP servers, and so on, storage. We have several different routes in and out from these locations. We have diesel backup from several generators. It shouldn't go down. And also, to be able to steer our sites or during the time, we take in time from all other sites also to be able to create one timescale. So we are creating 12 timescales using 12 clocks on each site. So you could call this a Swedish model. So we are in kind of a cooperation with RISE, the national NMI. They are doing the realization of the Swedish timescale. We have it traceable, and as for the moment, I have actually 3 guys traveling across Sweden doing calibration of our sites to be able to be sure that we are sending a qualified time. We have 6 redundant time nodes, but at 5 locations. I don't really like this. Stratum 1 servers, we have really good servers. So if you want to be sure that you have secure time, connect to our NTP server. We steer our timescales to UTC within some margins. We have both free and commercial services with SLAs. Yeah, we're using standard clocks, standard performance due to the lifetime, and we might upgrade them in the future. Also, I heard we have these FPGA-based NTP NTS servers that back in the day couldn't be spoofed or DDoSed. I mean, now I'm not really sure, so I need to figure out if they could be DDoSed. Due to that, we have higher bandwidth to our servers. Yeah, here's some of our services we are providing. We have the network P2P to ensure an accuracy of a couple of nanoseconds. If you're in need of less time, we have the network time direct. That's about 30 microseconds. We have network time remote. We are telling everyone that we can do a millisecond with that, or we guarantee an accuracy of that, of course. We have the free NTP service, and also we have NTS, which is actually a secure layer. So if you just set up your service either to NTS or NTP, if you don't want to have a direct connection through PTP to us, but we ensure that you have really, really good time in this kind of way. Yeah, you can access NTS servers at these sites. I'll come back to this. This is the most important slide today. So this is how we distribute time and frequency to the community. We're also working with optical fibers, and in this case, we did on-off keying in a coherent network just to see if we're able to distribute PDP in a good way. In this case, we used DMCs, dispersion compensating modules. It wasn't that good. I have some new data between Stockholm and Gothenburg, 690 kilometers. It only varies about plus minus 5 nanoseconds for that kind of distance. And that's in the case that the fiber is buried in the ground as well as power line fibers. So this is old data, but it's possible to actually distribute for long distances in a really good manner. So I have 2 slides left. We are working on a coherent transceiver for time and frequency with the aim of working for 10 to 100 gig. It should be able to distribute 1 PPS, 5 to 10, 100 megahertz. Should be easy, mounted in a 19-inch rack. Should be able to work with bidirectional duplex fibers. Should be able to distribute time and frequency in a sub-nanosecond range. Yeah, it should be daisy chained. We should be able to select wavelength. And hopefully we could set up and connect to the Southern European networks from Sweden, either through Finland or the Baltic countries, but that's our aim anyway. Yep, I'm also working on connecting the Scandinavian countries. So from a couple of days ago, we have a fiber connection between Finland and Sweden. And we are now working on connecting it to Norway. Questions?
Thank you, Mr. Sven, for sharing your experiences.